Now we'll use the characterization of regularity in terms of discriminant to answer our original question. Remember that originally we asked, given a quadratic space U, when is the canonical map from U to its dual space an isomorphism? This canonical map sends every vector V to map to the linear functional B of V. And the claim is that this map is an isomorphism if and only if U is regular. And to see this, it suffices to prove the following claim. We just need to claim that, let's say, the gram matrix of the bilinear form of A with respect to a basis EI is A. Right? Then we claim that if we select the basis EI on U and EI star the dual basis on the dual space of U, then this matrix is also the matrix of FB, of that canonical map. So before proving the claim, let's see why this claim would actually imply our proposition. Now, since A is the matrix of FB, we see that FB is an isomorphism if and only if A is invertible. Well, A is invertible if and only if its determinant is non-zero, and its determinant is just the discriminant of V by definition. So now what remains is to show that the matrix of FB with respect to these bases is actually A. So how do we compute the matrix of a linear transformation? Well, we apply FB to this basis element and write it as a linear combination of the bases of the codomain, right? So we need to know what these coefficients are. But observe that for any linear functional phi in the dual space, the expansion of phi in terms of dual bases is as follows. The coefficient of the dual of EJ is phi EJ. Why is that? How do we figure that out? Well, we just apply both sides, for example, to EI. Right? If we apply both sides, so we don't know this coefficient, if we apply both sides to EI, then this is going to be 0 except when it's equal, when the J is equal to I. So it picks out, so the coefficient in front of EI dual is just phi of EI. So in particular, we see that the coefficient here must be this FB of EI applied to EJ, but FB of EI by definition is just BEI, right? So I'll call this dot product, but it's not dot product, so, but it's just dot product with EI. So it's EI dot with EJ, and that is just AIJ by definition of the gram matrix. And so we see that this gram matrix is again the matrix of the linear transformation FB. So FB is an isomorphism if and only if this gram matrix is invertible, if and only if its determinant is non-zero, and that's if and only if the discriminant of V is non-zero, which is equivalent to U being regular. Sorry, here I use both the word U and V, but it should all be U.